Hey, good morning, sixth grade. Welcome to science class. I am Miss Adams, and I'm going to be with you for the next 5 weeks going over sixth grade science. I'm told we only have 25 minutes, so I'm going to jump right in. We're going to start with what I like to call housekeeping. Typically, I feel like it's good for students to kind of know exactly what we're going to be doing for the next few weeks. So let's kind of start with our standard. This is going to be what we're learning, the Sun, Earth, Moon system. The standard says we're going to create and manipulate models. So ultimately, everything over the next 5 weeks is going to have to do with the Sun, the Earth, and the Moon, and where they are in position with each other, their relative size to each other, and their relative motions, and then kind of what all that causes. So today we're going to start with a little bit of review for day and night, and then looking at the seasons. Looking ahead to the next few weeks, this is what we're going to cover. Today we're going to do seasons. Next week's going to be all about the model. Next week's we're going to be looking at the motions and the distance and the size. Week 3, we're going to get to phases of the moon, which is one of my favorite lessons. That's the AM-style lesson. And then 4 and 5, we're going to look at tides and eclipses. So let's kind of start right now. Let's talk about science journaling. All right, so I brought a couple of my science journals with me. If you don't have yours right now, why don't you go get something to write on? Whether that is your notebook that you typically use in your science class, or a science journal, or even just a piece of paper, whatever you've got. I also tell my students, we really like colored pens. When we start diagramming and sketching and putting stuff in the notebook, it's always helpful to do it in multicolor so you can kind of picture it in your mind when you're taking your test on the material. So ultimately, you can go grab that if you need to. But let's kind of jump right in with our models. Let's talk about rotation and revolution. I suspect these two words should be a little bit of review to you, but let's kind of talk about it right here with the globe. So when we're talking about rotation, we're simply talking about the spinning motion of the Earth on its axis. So there's no forward progress. This is just a spinning motion. And this causes on most planets day and night, because the side of the Earth that's facing the sun would be experiencing day, and the side of the Earth that's not facing the sun would be experiencing night. And as the Earth rotates, the day and night cycle occurs. Now, I hope you learned third quarter that that's not the case for all planets, because there are some planets that rotate at different angles so that they don't have day and night because of rotation, thinking specifically of Uranus. All right, so now let's talk about revolution, because this isn't the only motion that the Earth makes. So it's spinning on its axis. This takes about 24 hours. But then it's also revolving around the sun. As it revolves around the sun, we call that the orbit. That's the way that the Earth is moving around the sun. So the motion is going to kind of look like this. So the Earth is rotating, but then it's also revolving around the sun. I want you to notice something, though. Have you ever noticed when you look at a globe that it doesn't stand straight up? He's kind of like leaning to the side a little bit. He's tilted at a 23.5-degree angle. That's something I would write in my notebook. I'll be writing Earth's tilt 23.5 angle, half degrees is the angle. So he's tilted at an angle. That tilt never changes. The axis is stationary. Remember, the axis is that imaginary line that's running all the way through the globe. That axis doesn't rotate. It doesn't revolve. It stays stationary. Let me show you what I mean by that. So if we're tilted kind of like this, as the Earth starts revolving around the sun, we're still tilted like this. When I come over, now I'm behind the sun, I'm still tilted like this. When I get to the opposite position that I started, I'm still tilted in the same direction. The axis never flips. That's going to stay stationary. That is a key piece in our model. Remember when we talked about what the standard is, and the first 2 words of the standard talked about creating and manipulating models? In order for a model to be accurate and for it to portray the things that you want it to, then you need to make sure there are certain things about your model that are correct. And the first thing we need to pay attention to is the tilt of the axis, because this is going to matter. So we just established the fact that rotation is spinning on its axis, revolution is around the sun, rotation causes the day and night phenomena, and then revolution causes a year. So the amount of time it takes for the Earth to revolve around the sun takes about 365 days. I say about because I think that you've probably always heard there are 365 days in a year, but guess what? That's not quite right. There are actually 365.25 days in a year. There's actually 6 extra hours. It takes 365 days and 6 hours, and 6 hours is a quarter of a day. So 365.25 days for the Earth to revolve around the sun. What do we do with those extra 6 hours? Well, we just saw that 2 months ago at the end of February. That causes a leap year. We take those extra 6 hours and just totally ignore them for 3 years. And on the 4th year, we've got the 4th quarter of a day, and we add that extra day to the end of February and call it leap year. So revolution takes 365.25. I would probably write that in my science notebook, that's revolution of the Earth, 365.25. If I'm moving too fast for you, we're going to take the science notebook and take some notes at the end of this segment. So let me just I'm going to take a deep breath and tell you, I know that I move pretty fast, and I know that I talk pretty fast, and I know that I'm covering a lot of information right now. But my science classes are normally 51 minutes, and I only have 25 here. So I'm trying to throw as much at you as possible. So if you're not getting the notes, don't panic, don't stress out. We're going to have a minute at the end to be able to kind of recap and go over all that. If you prefer to just kind of sit and listen, feel free to do that too. All right, so now let's talk about, we've talked about the rotation and the revolution and what that model looks like. But let's talk about what that causes on Earth. What are the effects of Earth on the fact that it's revolving, rotating, and at a tilt? Well, it's clearly going to affect the amount of direct sunlight the Earth receives. And like when you think about it, this is something that I'm pretty sure you already know. The area at the equator gets the most sunlight. It's the tropics. Think about it. Think about what your mind conjures up when you think about going to the tropics. You think about summer weather. Well, guess what? It's summer there all year long. There's really only one season at the equator, because no matter where the Earth is in its revolution, the equator is always kind of pointing at the sun, getting the most direct sunlight. So look closely. With the Earth tilted away from the sun, the northern hemisphere right now is not getting as much direct sunlight as the southern hemisphere. Because with this tilt, that means that the sunlight is really hitting the southern hemisphere at a more direct angle. Let's talk about a misconception, because this is something I hear a lot, even in adults. So that revolution that we did around the sun, it's not a perfect circle. It's more of what we call an ellipse, meaning it's like an oval. And with an oval, there's going to be 2 points on that orbit that are further away and 2 points on that orbit that are closer. So when I was orbiting around the table and orbiting around the sun, this would be the long part of the oval where I'm slightly further away. And then in front of the sun or behind would be where I'm slightly closer. But summer and winter are not about distance from the sun. That 23.5 degree tilt we're talking about does not cause enough distance to matter. When we're talking about distance in space, that's not enough distance to matter with the speed of light. It's not about distance. It's about the angle at which the light hits the Earth. So back to our model. If the northern hemisphere is slightly tilted away from the sun, the angle that the sunlight is hitting the northern hemisphere is a little bit more down. That's why the days are going to be shorter. There's not as much time in the day. In fact, let's ponder that for a minute. There are 24 hours in a day. How many of them have daylight? How many of those hours have daylight? Typically, when I have a classroom full of you guys, the answers sound something like, well, there's 12 hours of daylight and there's 12 hours of darkness. Because if there's 24 hours altogether, then there should be 12 hours of daylight and 12 hours of darkness. Well, there are 24 hours in a scientific day on Earth as the Earth rotates. However, how much of that is day and how much of it is night varies. It changes, and it depends on the revolution around the sun. There are only 2 days throughout the course of the entire year for the temperate zone where we live to get 12 hours of daylight and 12 hours of darkness. And those are called the equinox. Hear the word equal and equinox? Equal daylight to darkness. So let's go back to this revolution model and let's talk about how that daylight to darkness and those equinox work. So we've got the Earth and he's got his same tilt. He's kind of tilted away. And when I'm in this position, and we're going to talk about the northern hemisphere. The northern hemisphere is pointed away from the sun. So he's at winter. When I get to this point in our revolution, the sun is in front of the Earth, and so this tilt doesn't affect the angle at all. All of the sunlight is hitting the Earth at the same angle. So for this day right here, there will be 12 hours of daylight and there will be 12 hours of darkness. It's going to be an equinox. So we had winter, now we have an equinox. When we come over here, look at the angle now. We're tilted towards the sun. So now our northern hemisphere is having summer because now the direct sunlight is hitting the northern hemisphere. Now, I always tell my students, I like these little tricks in my brain that help me remember things, and I think opposites are kind of easy. My brain always kind of wants to sort things into categories, and opposites is one that I use a lot. We would call winter and summer opposite positions, right? They're like the exact opposite. We're 180 degrees, like in the math of the orbit of where we are, we're in the opposite position. We're also in the opposite season. Summer and winter are opposite seasons. If this is summer, as we continue through our revolution and we're ending up in front of the sun now, what season comes after summer? Fall. Think about it. I always tell my students, after summer break, we go back to school in the fall. This is also going to be an equinox. With the Earth tilted this way, we're not tilted towards or away from the sun. The direct sunlight is hitting the Earth at the same angle. So this is going to be an equinox. So our opposite positions are going to be fall and spring are your equinox. 12 hours of daylight, 12 hours of darkness. Then winter and summer are opposite, and they're going to be what we call solstices. Now this is what's interesting about the solstice. So if we had 11 hours of daylight on the spring equinox, and we had 12 hours of daylight on the spring equinox, and 12 hours of darkness, and then 12 hours of daylight and 12 hours of darkness on the other equinox, your solstices are going to be the days where you have either the most amount of daylight or the least. So in this position, if we're at winter, this winter solstice is going to be the shortest day of the year in terms of relative daylight. So like every day has 24 hours, but how many of those 24 hours are daylight and how many are darkness? Well, in this case, we're going to have the shortest day of the year where we have the least amount of daylight. When we get over here to summer, and I got to speed things up because we're running out of time. All right, so if I'm over here at summer, this solstice is going to be the longest day of the year. This is usually like June 21st. If that happens to be your birthday, if you're a June 21st baby, your birthday is typically the longest day of the year in terms of relative daylight. So the longest day of the year, we call that a summer solstice, and that's going to be the most amount of sunlight we receive. And then every day as the Earth is orbiting the sun, the daylight is getting less and less and less. If we just had the maximum amount of daylight right now, then the very next day, we can't have more daylight or that wasn't the max. So if this was the maximum amount of sunlight we can have, then the next day, we have like a couple of minutes less. And the next day, a little bit less. And then a little bit less. And then a little bit less. And then a little bit less. And a little bit less. Until we get to the equinox where we have 12 hours of daylight, 12 hours of darkness. The very next day, now we're going to have more darkness than we have daylight. More darkness than daylight. More darkness than days are getting shorter. Days are getting shorter. Days are getting shorter. Days are getting shorter. Until we get to the solstice, where now this is the shortest day of the year. There are the fewest amount of daylight hours. The very next day, we're going to start to gain daylight. Get a little bit more daylight, a little bit more daylight, a little bit more daylight. All right, let's try to take a few minutes to get some of this in our notebook. So I've got to change my cords out. Give me 2 seconds. You can be getting your notebook out, getting your pens ready. And let's get the document camera going so you can see my notebook. All right, so here's my science notebook for third quarter. That is artwork of one of my students. Shout out to Quinn. Thank you very much. And I'm going to open to a clean sheet in my notebook. And let's talk about a couple things. I'm actually going to turn mine this way because we're going to draw a diagram. Let me preface this by telling you guys, I am no artist, but I don't let that stop me. It's not necessarily about being perfect. It's more about making sure we get our information correct. So let's start with our sun in the middle. Boom. I'll even give him some sun rays. I'm going to date this Wednesday, 4/15, and I'm going to say sun, earth model. All right, here's our sun-earth model. So I'm going to draw 4 earths around my sun, and I'm going to draw my axis, and I'm going to keep my axis consistent throughout. Remember we said that's going to be a key part in any model, is making sure that the details are accurate. And the biggest mistake here is to flip the axis and then it doesn't work out. So there's my equator, so we can see the northern hemisphere from the southern hemisphere. And we're going to be identifying the northern hemisphere because the northern and southern hemisphere are opposites. They're going to be in opposite seasons. So here, I've got the northern hemisphere, and his axis is pointed away from the sun. So this season is going to be winter. And then I like to go opposites. So if that's winter, the opposite to that is going to be summer. And if we are orbiting this direction, after summer, this is going to be fall, which we also call autumn. And the opposite of that is going to be spring. Autumn and spring are our equinoxes. These are those days where we have equal amounts of daylight and equal amounts of darkness. So we're going to call this one the autumnal because we're taking the word autumn and we're going to make it an adjective and call that the autumnal equinox? This is going to be spring or the vernal equinox. Winter is a solstice. Summer is a solstice. I really intended on finishing this up with some definitions on this note page, which I will absolutely do, and I will post it somewhere for your teachers should they want to access it for you. I'm being told that we're getting close to the end of our time, so I want to wrap this up with a couple of words for you. The first one is, when we were talking about daylight to darkness, you can track this. See if through the next week, before I meet you again next Wednesday, see if you can notice the trend right now. Are we losing daylight or are we gaining daylight? What time is the sun setting or what time is the sun rising? You can do this by going outside and taking notes in your notebook. Go outside and be kind of waiting. What time does the sun go down tonight? Then check again tomorrow night. Check again the next night. Are we talking a minute every day? Are we talking 2 minutes every day? How much time are we losing or are we gaining time right now? So spend the time the next 7 days before I see you again, seeing if you can answer that question. If you're able to use the internet, you can even look this up. There are websites that will show you over the course of a year for different places what time the sun rises and what time the sun sets. And you can see how much time is gained or lost. Next week, we're going to do nothing but modeling, but next week we get to bring the moon into it, which is kind of one of my favorite standards when we get to talk about the moon and where the moon is and how it relates to Earth. Until then, I thank you for your time this morning, and I look forward to seeing you next week.